Hi everyone, we're going to be looking at the collision theory, and this theory helps to explain why chemical reactions occur. So according to this theory, for a chemical reaction to occur, these three conditions must be met. So particles must collide. They must also collide with a proper orientation, and they need to have a minimum amount of energy for the reaction to initiate. And this energy is called the activation energy. So if you look at these two examples, here you have an example of a successful collision where A and B, molecule A and molecule B, are coming in contact here. So A and B come together. So the bond between A and A breaks, and the bond between A and B forms. And for this to happen, the molecules must come in contact, and they must come in contact in the proper orientation. So A and B must be aligned, and they need to have sufficient energy to break this bond over here. So A and A must break, and B must break for the reaction to actually occur. If you still remember, bond breaking is an endothermic process. It absorbs energy. So delta H is positive, which means that for the bond to actually break here, for A and A to break, there must be energy in the system. So it's going to absorb energy in order to break the bond between A and A. And then energy is released when A and B form, because bond formation is exothermic. Now, number one is an example of a successful collision. So the particles have sufficient energy to break or rearrange chemical bonds to transform into products, and the particles collide. They collide with appropriate orientation. These three conditions is present for something to be a successful collision. Number two is an example of an unsuccessful collision. So they are coming in contact, molecule A and molecule B are coming in contact, but they are not in the proper orientation. So A is not next to B. So A is in between B and B. So it's not the proper orientation. So there's no possibility of a reaction. So particles collide, but they bounce off, or they do not have sufficient energy to break the chemical bonds. So these two are examples of successful and unsuccessful collisions. So if we're able to get more particles to collide, we're going to have more particles colliding in proper orientation. Hence, rate of reaction would increase because there would be more successful collisions. If we find a way to increase the energy of the particles, definitely there's going to be more particles with that activation energy. Therefore, rate will increase. So if we look at the kinetic model theory, it tells you that gas particles, they are constantly moving, and that the kinetic energy of the gas particles is proportional to the absolute temperature of the gas, which means that, which comes back to the equation that we did before, where kinetic energy is directly proportional to temperature, and temperature is in Kelvin, so it is absolute temperature. At 0 degrees, there's no movement, so there is no collision, technically. And when temperature increases, particles move faster. They exchange energy with each other through collisions. And the more energy there is, the greater the likelihood that the particles will collide with energy equal to or greater than the activation energy. So if we have to write this, we would say energy of particles are greater or equal to activation energy. This needs to be satisfied for any collision to be successful. And the more particles you have with energy greater or equal to kinetic energy, the more successful collisions you're going to have. So any factor that increases the rate of successful collision will increase the rate of the reaction. Okay, now let's explore a little bit activation energy. Now, activation energy is the minimum energy that colliding molecules need to possess for a successful collision to happen, and this successful collision will definitely lead to a reaction. This is the definition according to the guide. You have to know this. You can be asked, what is activation energy? Let us see what is actually activation energy when we look at an energy profile diagram. So we have two energy profile diagram. There's a little mistake in this diagram. You please correct it. So this arrow should go only upwards. Okay, this is delta H, and this arrow should go only downwards. This is delta H as well. So this is an endothermic reaction where delta H is positive. So here energy is absorbed. So you can see here energy of reactants, energy of products. So products have more energy than the reactants. And this one here is an energy profile diagram for an exothermic reaction. And here energy is liberated or energy is released. Okay, so delta H here is negative. You can see it going down. Now, in this energy profile diagram, you can find the activation energy to be from the level of the reactants to the peak here. So the activation energy is always going to be from the level of the reactants to the peak. So this is going to be activation energy. And the activation energy is actually the energy gap between the reactants and the transition state. So this is called the transition state over here. And this state is a very unstable state where some of the chemical bonds are broken or weakened, and some of the bonds are starting to be formed. So this is a very unstable state, and this state can actually not be isolated. You cannot get it. You cannot isolate this state because it is an unstable state. So the level of the energy gap between the reactants to the transition state is the activation energy. You're going to attempt this question here and answer in the box. Pause the video, work it out, and then you check your answer. First thing, you're going to have your axes. This has to be reaction progress. This is very important. You have to label your axes, reaction progress, and this is going to be energy. The y-axis is the energy. If your axes are not labeled, label it. And here, the delta H is negative 10, and this shows that this is an exothermic reaction. So exothermic reaction, reactants are on top, products are down. So that the difference between these two is negative 10. And the activation energy is 20 kilojoule per mole. So then the activation energy is going to be from here. So it's going to be from here to here. This is activation energy. This is going to be 20 kilojoule per mole. And if you look at the arrow, you see this one, this is delta H negative. It goes down, so from reactants to products. And activation energy, it goes up from reactants to transition state. Okay, the arrow is never going to be double arrow as it was here. So it's always one-sided. So this is done. Second question, deduce the activation energy for the reaction C plus D giving A plus B. So it is the reverse reaction. So if you look at the reverse reaction, if we were to draw, you don't need to draw, but just to make you see how it's going to be. If you were to draw it, it would be C plus D giving A plus B. Right? It would be like this. And we saw that this part is minus 10. So this part is going to be 10. And the part here, this is 20. So this part is going to be 20. Therefore, activation energy is always from reactants to transition state. This is a transition state. Okay, here, this is the transition state here. Therefore, activation energy is going to be 10 plus 20. So this is 30 kilojoule per mole. So here it's asking you to deduce. So there's no diagram, that's not needed. So you can deduce it to be 30 kilojoule per mole. Now, whenever we're looking at a substance, the particles of any substance is continuously moving because they all possess kinetic energy. But they don't all have the same kinetic energy. They have a range of values of kinetic energy. So average kinetic energy, so we are averaging the kinetic energy of all the particles. That average kinetic energy is directly proportional to the absolute temperature. Now the Maxwell-Boltzmann distribution curve, it tells you the number of particles, number of molecules or particles according to their kinetic energy. So we can see here, if you look at the graph, so it crosses 0, 0. This is very important. So there's 0 particles having 0 kinetic energy. So all the particles are actually moving. The curve will always have a peak like this. Here, it will always peak like this. And then it will go down, which means that there is less particles with high values of energy. And here, this is the activation energy. And the shaded part over here tell you the number of particles that have energy greater or equal to activation energy. So these particles would actually react during a reaction, and these particles will not react. Now, as temperature increases, what happens? When temperature increases, the energy of the particles increase. So there's going to be more particles with high value of energy. So that peak here, it shows the number of molecules with high value of energy, the highest value of energy that the particles have. Now, when you increase the temperature, the maximum number of particles will have higher energy. So the peak is going to shift like this. So we're going peak shifts like this. So the number of molecules with high value of energy increases, so the peak shifts, and the number of particles with energy greater or equal to activation energy also increase, right? So the more you increase the temperature, the curve flattens and broadens, so the maximum shifts to the right because you're going to have more particles with high value of kinetic energy, and the proportion of particles with activation energy, with energy equal to or greater than activation energy increases. So you can see that here it's only the green region, it's only this proportion that has enough energy to react. But when you increase temperature to T2, it's this proportion that has enough energy to react. So you have more reactive particles. Okay, so in the graph above, you're going to sketch a third curve at temperature T3, where T3 is less than T1. Pause the video and sketch, and then you play again. So if T3 is less than T1, So there's going to be the energy, the kinetic energy of the particles. The maximum kinetic energy of the particles is even going to be lower. So the peak is going to be more to the left. It's going to be steeper like this. So it's the black curve where this is T3. T3 is less than T1. So it is to the left, and the peak is higher than T1. So when temperature increases, the peak flattens and moves and shifts to the right. Okay, so this is what happens. Now predict with reference to kinetic energy and activation energy whether the proportion of reactive particles will be lower, higher, or the same. So definitely you can see here it's going to be lower. So we can see here that the average kinetic energy of particles for T3 will be lower than for T1. There will be fewer particles that will have kinetic energy greater than activation energy. So the proportion of reactive particles for T3 is going to be less than for T1. So I made reference to average kinetic energy and activation energy as asked in the question.